Thanks for attending my talk. My name is Jimbo, and today I will be presenting my work, Synthesize Fair Decision Trees via Iterative Constraint Solving. This is a joint work with Yannan and Chao. Bias against demographic groups have raised a lot of concerns. People start to pay more attention to the fairness of machine learning models. In my talk, I will first introduce the background and then talk about our method and experiments. Typically, during the training phase, we take the training data and feed it to the learner in order to produce a prediction model, which is a decision tree here. While in the test phase, we take the test data and as input and generate the predicted output. At the same time, we may also want to verify if its predicted output satisfies fairness metric. In this work, we focus on the learning procedure and propose a synthesis algorithm to generate a fair classification model. The first existing approach is based on pre-processing, and basically they focus on debiasing the training data, but this technique fails to eliminate the bias introduced by the learning algorithm. Another approach is a post-processing approach that can remove such bias by modifying the predicted output. However, this result is often hard to predict and may decrease the text accuracy. In this work, we focus on the in-processing technique, which aims to incorporate the fairness metric into the learning algorithm. In-processing techniques for learning a fair decision tree fall into two categories. State-of-the-art algorithm is a greedy search technique, which incorporates fairness into its entropy calculation. However, it lacks a fairness guarantee, and this incorporation is often unpredictable. Another line of work is to formulate the decision tree learning as an optimization problem. However, this approach remains theoretical due to its limited scalability. Only our method can solve both problems. To overcome the limitations of the existing approaches, we propose an iterative constraint solving technique. We capture the decision tree with adaptive depths and then encode the accuracy and fairness constraints to make the fairness accuracy trade-off not only predictable, but also easy to explain. Instead of encoding the decision tree as a monolithic ML formula, we break it down to a series of small steps to avoid the scalability bottleneck. Thus, our method is efficient and scalable. Next, I'm going to give a brief background on fairness. Assuming that we have a decision-making model with two subpopulations, majority and minority, and they are both being fed to the decision-making model, which decides whether or not to accept an application. And we want to make sure, in this context, decision-making model is not discriminating against the minority. To formalize this setup, we have a sensitive feature indicating whether they are from the majority or minority. Here, input X is represented by a list of features, and we also define the binary classifier T. And in this context, there are a bunch of fairness properties proposed in the literature. In this talk, I will be focused on demographic parity, and our technique can also be applied generally to other fairness properties. Demographic parity is a property which basically says that majority and minority members should get positive outcomes at roughly the same rate. And just to formalize that, we first define the acceptance probability. This is the probability that a member from the subpopulation has a positive outcome. And the classifier T satisfies the demographic parity if the acceptance probability for majority and minority satisfy this equation. After introducing the background, I will start to give you a general overview of our method. Internally, our synthesizer encodes the hierarchical structure symbolically, along with the accuracy and fairness encodings. Then we apply domain-specific optimization to pre-process these formulas. Later, given this optimized formula, we use ML solver to compute the optimal feature f star. Afterwards, f star is used to partition this dataset. We iteratively partition these nodes until it satisfies a termination standard. Externally, our synthesizer takes the training set and sensitive features as input and synthesize a fair decision tree as output. Here we demonstrate how the iterative constraint solving works with steps k being 2. We first encode the symbolic constraint inside this red box and obtain the objective O together with the constraint phi. Both O and phi consist of 3 subformulas, which we will describe later. Then they are fed into the ML solver, which produces the best split feature f star. F star is then used to split node 1, and then we can remove this red box to the next tree rooted at node 2. In the second iteration, we start from the root node 2 and repeat this procedure to split node 2 and iteratively solving these constraints with steps k. This red box represents the symbolic tree, which needs to be encoded. We use V to denote the set of branch nodes and L to denote the set of leaf nodes. Since the decision tree structure is not known to us, we encode a symbolic binary tree by allowing all the branch nodes and leaf nodes to be either activated or deactivated. To encode this activation information, we introduce decision variable P. It equals to 1 if the branch node V is activated and has a split. Otherwise, it equals to 0. We also introduce decision variable LL to denote the accuracy loss. Our objective function aims to minimize the accuracy and the tree size while maximizing the fairness. The constraints on the tree size is to avoid overfitting. The reason is because a smaller tree is less likely to overfit. Before we optimize the objective, we also have to satisfy the constraint phi, which must be encoded as a conjunction of equality or inequality constraints. These constraint formulas phi share the same variables as their objective function. The objective, together with its constraints, will be solved by an off-the-shelf ML solver. Now we will first introduce the challenges for encoding the tree structure. Given a symbolic tree, features F1, F2, and F3 are used to split node 1, 2, 3. To formally encode the relation between the branch nodes and its corresponding split feature F, we introduce another indicator variable WVJ. It defines if a feature J is used for splitting node V. But now we can formulate the symbolic feature FV by multiplying the weight vector W with our input vector X. In addition, we are still wondering the relations between the input X and the node. Therefore, we introduce a new decision variable Z, which monitors this relation. For example, Xi flows to node 7, Zi7 is 1. Intuitively, input I can only flow into exactly one leaf node. The reason is because each input Xi will only satisfy one path constraint in a decision tree. To summarize, if Xi satisfies the left branch condition, it flows to the left child. Otherwise, it flows to the right child. We need a constraint phi to capture these 2 scenarios. Also establish the relations among these decision variables. The straightforward way to encode these 2 scenarios is using disjunction operators. However, ML solver does not allow the use of disjunctions in its constraints. To address this challenge, we have to linearize this logical constraint. Here, we figure out a unified formula to encode these two scenarios with left child Zi2 being either 1 or 0. Therefore, we introduce the subformula to unify both cases in one constraint. The unified formula adds another slack value to make it hold for both cases. The unified formula for the right branch is similar to that. There are more detailed constraints for encoding the tree structure, and please refer to our paper for more details. Now we'll introduce the challenges for encoding the accuracy. Given the constraints of the tree structure, we formulated the accuracy by the misclassification error. As we consider a binary classifier, the output label is either true or false. Misclassification error is defined as the number of examples in node L minus the number of examples that have the most common label. For instance, leaf node 4 has 8 examples. The number of examples with true label is 5, while the number of examples with false label is 3. Therefore, given the total number 8, the number of examples that have the most common label is 5. As a result, the misclassification error is 3 for this leaf node. The most challenging part of accuracy encoding is to model the number of examples with the most common label. As we have noticed, ML solver does not support max operators expressed in its constraints. Then we are required to linearize these constraints. In order to do that, we introduce a new Boolean indicator variable to decide if a leaf node L is associated with label M. Then we are able to model this information. Now we'll introduce the challenges for encoding the fairness. Here we focus on the demographic fairness. We have to compute two acceptance probabilities. Our first step is to rewrite the acceptance probabilities. For instance, P minority equals to S0 plus divided by S0. We use an example for demonstration. We use blue box for minority and yellow box for majority. Here we have two leaf nodes associated with positive label and negative label respectively. Each leaf node is also associated with a subset of input data. We first calculate S0, which is a total number of minority groups. In addition, S0 plus represents the minority group with positive output label. The result of this division is the acceptance probability for the minority group. In order to encode the fairness properties, our first step is to encode S0, which is counting the number of minority. Therefore, we define indicator variable S0i to represent the minority. If xi belongs to minority, then S0i is true, otherwise it's false. We then encode S0 by counting the number of S0i over all the inputs. However, the definition of S0i is disjunctive, and the ML solver does not support that. Hence, we need to come up with a linearization to encode these logical constraints. Meanwhile, we also need to introduce a new Boolean variable to compute the value of S0 plus. If input xi belongs to minority and it also has a positive output class, then this indicator variable is true, otherwise it's false. Similarly, we also have to linearize its constraints for defining S0IL. Furthermore, our framework is also flexible to encode other fairness properties as well, such as equal opportunity. Due to this limited time, I will not introduce the details. Now we'll introduce the domain-specific optimizations. Given n training examples and a depth k binary tree, the complexity of constraint solving is related to both n and k. As k increases, The look-ahead window also increases, resulting in a more optimized tree. However, it also increases the complexity and the solving time. Therefore, there is a trade-off between looking further ahead and reducing the constraint solving time. Based on this, we propose optimization to choose K's value adaptively. Additionally, we also sample training data on demand for further optimization. Considering two extreme cases, when K is set to a sufficiently large number, our method becomes monolithic constraint solving. In contrast, if we set the K's value to 1, it downgrades to the heuristic-based method. The look-ahead search is disabled. In summary, our approach unifies these two techniques. Now we will talk about the experiments. We have implemented our algorithm in a tool called SF-Tree, where we focus on evaluating two aspects of its performance. First, we evaluate the quality of this tree, which consists of the fairness and accuracy metrics. Second, we evaluate its scalability. We mainly compare with the two fairness-aware learning approaches, one for heuristic-based, named IGCS, and the other for the constraint-based approaches, named MIP. We also compare with the original cards for quantifying how accurate we are. We split our benchmarks to small and large categories. They are used for evaluating the quality and the scalability. We first evaluate the quality of our approach on a small dataset, where MIP is able to finish. The left figure denotes the accuracy. CART is always the most accurate one, and our method is very close to it. While the right figure represents the fairness data, this red line represents the fairness threshold from the literature. MIP is always the most fair version, while our method is very close to it. We also evaluate the quality of our method on the large dataset, where MIP times out. On the left-hand side, the card is still the most accurate, and our method is very close. On the right-hand side, our method always satisfies the fairness for all these three large datasets. In terms of the scalability, MIP times out in all the large datasets, while our method is able to finish within 1 hour. Therefore, our method runs more than 10 times faster than the MIP, while IGCS and CART fails to satisfy the fairness due to their limited ability to look ahead. In summary, our method is the only one that can produce a fair and accurate decision tree for datasets with more than 40,000 training samples. To summarize, SF-Tree is able to synthesize a fair and accurate decision tree, and is also scalable, explainable, and flexible. In future directions, we plan to adapt our iterative ML solving framework to check other interesting properties beyond the fairness. Thanks for attending my talk, and I'm happy to take any questions.